Okay, the next block of problems, the next four here, 31 through 34, involve using integration by tables. Now, what I do for test purposes is I don't provide the big integration of tables. I pretty much provide the formula, or sometimes I've been known to provide like two or three similar formulas, and you have to pick the right one. Usually, but a lot of times I'll give you the formula that you'll need to use. You won't have to go through an entire table looking for it. However, that doesn't always make it easy to get 100% correct. You still have to consider what people don't consider as du issues, when you're getting the final answer. But with that being said, let's jump down here. I think this first one I decided was pretty bad, so I eliminated it from consideration. Yes, 31 omit. I think I decided that it was bad news. But you see how I have these formulas labeled. That's, like I said, that's not what I'll do. I think if you look at my notes, this probably needs to be revised a bit. I would literally say, evaluate this integral using the formula. Let's see how quick maybe I can find it. It doesn't take too long here. I'll tell you what. So you wouldn't see a situation like this where it was numbered formula 84. I just figured for the time being, you would have been able to look that up. I probably should have put the problems in. That's all right. But on a test, I absolutely would put the formula next to the problem. But let me show you what I mean. See, in other words, this number 84 right here, you just would have, I would say, integrate this using, this formula right here. But here's where, I'm talking about is you got to be careful to be able to get this perfect. So you use that form right there. So you have to identify what u is. So obviously u would have to be the exponent 9x squared. But du is 18x dx, and which means you have to adjust for a 1 over 18. And it looks like I made a mistake here, that this 1 over 18 then should also be part of the answer. I just forgot to bring it over. And okay, well, let me fix this first, and then we'll discuss what happened here. Yeah, just after I got through talking about it, I had it. Anyway. So then you would follow that formula, u minus natural log of 1 plus eu, but you have to take the 1/18th into consideration as part of your answer. So these aren't that difficult. Well, some of the integration formulas can be difficult if they involve, repeated use or something, they're what they call reduction formulas. But for the most part, I don't like these to be too complicated. So but you have to adjust for the du to get it exactly right. That's what you're going to have to do on a test. So it's not, a lot of people will just look at that formula and they'll just plug in 9x squared for u and not even take that into consideration. So you've got to take the du into consideration. So this one says it's formula 17. So let me find that one formula. Like I said, you would have that next to the test, next to the question on the test. Yeah, I won't be giving this entire sheet here. What you won't need to, because I'll give you the right formula that you need. Oh, this one's kind of interesting. Presents a little bit of a challenge, I guess you might say. You have to choose which one of the two formulas is correct, based on whether A, which this number right here under the radical, is that positive or is that negative? That's how you choose which one of these two to use. All right, so that still won't be too bad. At least it gives us some sort of challenge. Let's see what we have here. Okay, it's just written in a different order. Be careful with that too. You know, x minus 4 is the same thing as negative 4 plus x. In fact, I think what I'm going to do here, so I'll keep going back and forth, which is what I should have done. Let me go back to the, yeah, now let me snip that out. Let's see if I can squeeze that in there. Even if it's small, I think you should be able to zoom on it. Should have put these next to the problem to begin with, like they will be on the test. Okay. And then I'll do the same thing for the last one too. Alright, so there it is. Well, I'm pretty sure I wouldn't squunch it up that much. Let me go and put this one here while I'm at it. Go back to 84 real quick. Formula 84, which is right there. We'll snip that out of there. And there we go. Ooh, really might have to shrink this one in there. Well, actually, I think I can take where it says Formula 84 and wipe that out now. Whatever I did there, I want to undo. Something moved on me. Let's shrink it for a minute. Then I'll just erase this. Okay. Well, like I said, the numbering of the formula is not going to be a concern for you. I would give you that without the number 84 there. But you know what you have to read on this one, maybe I'll move this over a smidge here, is you've got to realize that when you're looking at this formula, you know, at least you know, even though it's two choices, you can still see on the left side generically what the basic thing is. Now remember, with addition, the order doesn't matter. So plus for plus, so it's kind of, so you see that says A plus BU, but BU plus A would be the same thing. So in this case it's plus, but minus means it just makes that A negative 4. So obviously that's very important because of which one of these two you choose. No problem. It's going to be that negative A. It's going to be the bottom one. So the U is X here, so there's no adjustments for DU on this one. It's not as much fun. Actually, I guess the challenge on this one was picking the right formula. But usually I like for it to be an adjustment for the DU. So DU is DX, so no adjustment. A is negative 4, and B would be 1, because the coefficient of X would be 1. So you see 1U, and then you have the U of X on the outside. You plug it right in. 2 over the square root of negative A. You might think, hey, it's going to be imaginary. Remember, A is negative, so it's going to make it positive. 2 over positive 4, square root of 4. That'll cancel. It's 2 over 2. Arctan of X minus 4, A plus BU, over the negative of A, which will then be positive 4, all under the radical. This is fine. That would have been okay to leave it the way I left it, but I went ahead and that's the same thing because you can split that up as 2 square roots for division, and the square root of 4 on bottom would be 2. You can't do anything with that X minus. You can't adjust that. But division, I can split them up, but I didn't have to. That takes care of that one. Number 34, to make it fit this formula 40, which I'll dig out right now. Alright, so let's snip this out of here. Alright, so this one makes it, as an interesting algebraically because of having to complete the square to make it fit. Because you can see from the formula with u squared being on bottom in the interval that there's no doubt that u has to be x minus 1 to make it fit that. So that kind of gives you a clue that when you complete the square, you're going to have u will be x minus 1 when you complete the square. So it gives you a little... All right. So this kind of goes back to chapter 5 stuff when we were doing the completing the square. So you pull out a negative, so it leaves a negative x squared minus 2x, and we add 1 on the inside. But remember, whenever this was a negative factored out here, the negative affects the plus 1, makes it negative 1, so it needs to be a plus 1 here also. So whenever it's a positive, you go plus minus. When it's negative, you go plus plus. So plus 1 makes out a 4, and it ends up being 4 minus x minus 1 squared, like we know it needs to be. And so let's kind of piece all this together now. Now we have everything set. We know that u is x minus 1, du is dx. No adjustments there. A squared is, so once again, this problem, I don't mind that there was no adjustments for the du since you had to complete the square. That was challenging enough. The a squared is 4. That makes a 2. U is x minus 1. So we're good. And it's the negative of the radical. Okay, whatever the answer key said. Okay, I'm assuming it must have. So yeah, I mean, same thing. If you multiply by negative 1 over negative 1, the answer must not have this negative in it, and it might have 1 minus x on the bottom, which would be the same thing. If you multiply by negative 1 over negative 1, which is not mathematically necessary. But I'm going to take a quick peek at it here. This is number, what is it? Where are we here? 34. Yeah. So you multiply top and bottom by negative 1, from our answer, you get this answer. So with that being said, let's jump back up here and look at the rest of this problem. Not much left to look at. Just follow it. And then it's going to be minus arc sine of u over a. So minus arc sine x minus 2. 1 over 2 plus c. There we go. Now we're starting the section on the L'Hopital rule problems. Let's take a look at number 35. If you plug 0 in here, you're going to get 0 over 0, I believe. Yes, because 0 over 3 is 0. E to the 0 is 1, so you'll get 3 minus 3 on top, and that's 0 over 0 on bottom. So L'Hopital's rule. Now, when you take the derivative of x to the 1/3, e to the 1/3 x, the chain rule says you'll then have a derivative of 1/3 on the outside. So that's why the 3 is canceling. So 1/3 times 3 cancels. So it's just e to the x over 3 minus the derivative. See, the derivative of x is positive 1, but you have the minus in front of the parentheses, so it makes it negative 1. The bottom is going to be x squared. Derivative is 2x. And you put 0 in there, you get 1 minus 1 is 0. You get 0 over 0 again. That means you can apply L'Hopital's rule again. So then the derivative of e to the x over 3 would be 1/3 e to the x over 3. Now we have 2 on the bottom, so we know we're not going to get 0 over 0. I put 0 on the top. I get e to the 0, which is 1. I have 1/3 divided by 2. Therefore, this limit will equal 1 over 6. Okay, I don't know why I have so much blank space here for that, but okay. So I'm going to worry about fixing it now. Infinity, we have infinity over infinity, so that's one of the L'Hopital's rule forms. So take the derivative of the top, which is 2x, over the derivative of the bottom, which is 1 over x. Flip the 1 over x over to the top, and you have 2x squared. So now it's not even a fraction anymore. You have the limit of 2x squared as x goes to infinity, and that's clearly going to infinity, which means it diverges. Number 37. Put in 1, you're going to get 0 over 0. L'Hopital's rule, take the derivative of ln of x is 1 over x. X minus 1 is 1. You put 1 in there, you're going to get 1. So that one's not too difficult. Next one, you have infinity over infinity. So L'Hopital's rule, take the derivative of ln of x, which is 1 over x. The derivative of x cubed is 3x squared. You can resolve this if you want to into one fraction, but which maybe I should have done, but that's okay. This is still correct. But if you did, it would be 1. You could drop the x down. It's 1 over 3x cubed. So as x goes to infinity, 1 over 3x cubed is clearly going to go to 0. So maybe I could have put one more step in there. 39. Infinity. Yeah, infinity plus infinity, still infinity. Over infinity on the bottom. L'Hopital's rule, derivative of the top is 1 plus 2x. The derivative of the bottom would be 6x. That's still going to be infinity over infinity. L'Hopital's rule again would be 2 over 6, which is 1/3. But let me show you a little trick on this one. And it kind of goes back to stuff in Cal 1 with limits at infinity. Yeah, this is probably not likely to put this one on an exam because it really does revert back to Cal 1. But actually, you see, even though it's written in a different order, x squared is the largest term on bottom, x on top, 3x squared on bottom. So they have matching exponents, square and square. So anytime this is only true is if you're going to infinity. That means you can just take the ratio of the coefficients. So it was going to be, no doubt, that answer was going to be 1/3. Yeah, because that's why, like I said, even though I wouldn't have this on a test, but if that was, x to the 10th over 3x to the 10th, yeah, you don't want to sit there all day doing 10 L'Hopital's rules or whatever when you can just get 1/3 real quickly. All right, so now we have x approaching 0 from the right. That shouldn't affect anything, the right and the left. There'll be some functions, like if you're doing a natural log and it's approaching 0, it can only approach 0 from the right, so it would have to be written as a plus. But that doesn't affect the calculation of the problem. You still evaluate it the same way. But this one, though, you can approach sine, 0 from both sides. So I don't know why they didn't just leave it as a regular limit, but that's all right. So you got 0 over 0. When you put 0 in here, L'Hopital's rule, derivative sine of 2x is 2 cosine of 2x, because of chain rule. 2x on bottom, reinsert 0. The cos of 0 is 1, so you'll get 2 over 0, which that's pretty much infinity. Positive infinity. Next one, put in 0. You're going to get 1 minus 1, which is 0, over 0. Take the derivative of e to the x as e to the x. The derivative of e to the negative x, however, is negative e to the negative x. So be careful with that, because the derivative of the exponent would be negative 1. So that's why the derivative of the e to the negative x is changing that negative to positive, because you're producing a new negative that's changing it to positive. Sine, of course, is cosine. Put in 0, you get 1 plus 1 now is 2, and cosine of 0 on the bottom would be 0. 1, excuse me. Cosine of 0 is 1. 2 over 1, so that limit would be evaluated would equal 2. Number 42. Sine of 2x over 4x squared minus pi squared as x goes to pi over 2. Sine of 2x, 2 pi over 2 would be pi. Sine of pi is 0. Now in the bottom, you put pi over 2 in, you get pi squared over 4. So that multiple of 4 will kill the 4 on bottom, which leaves you pi squared minus pi squared. There's your 0 on bottom. So it looks like I labeled that one. Derivative sine of 2x would be 2 cos of 2x. Derivative of the bottom. Remember, pi squared is a constant, so its derivative is 0. The derivative of 4x squared would be 8x. So you put in pi over 2. Cosine of 2 times pi over 2 is cosine of pi. Cosine of pi is negative 1. 2 times negative 1 will be negative 2. On the bottom, 8 times pi over 2 is 4 pi. So you have negative 2 over 4 pi, which is correct. But then that also would reduce to negative 1 over 2 pi. So that would be your exact answer for that one. The next one, you have the indeterminate form of 0 times infinity, because e to the negative infinity is basically 0. ln of infinity is infinity. So whenever you have 0 times infinity, that doesn't mean the answer is automatically equal to 0. If you go back and look at my notes and other problems, it's going to be 0 this time, but it's not something you assume. It's always 0. So what happens is you have to drop one of these things to the denominator, one of those two terms, because you want to get it as a fractional form to be able to use L'Hopital's rule. And in my notes and in class and whenever I talk about this, rule number 1 is we do not drop natural log. It's a little bit different when you have trig functions, because sometimes the trig function might drop, sometimes it might not if ln's not involved. In this case, ln's involved, so not ln. So that means e to the negative x on top is the same as e to the positive x on bottom. So we have ln of x over e to the x, which is infinity over infinity. Do L'Hopital's rule, ln of x is 1 over x, e to the x is e to the x. I could have dropped the x down to the bottom, but you're basically looking at 0 over infinity, so this does go to 0. But not all 0 times infinity is automatically equal 0. We definitely saw that in class. That's not always true. So how about number 44 here? I'm just looking ahead to see what we got here. Yeah. Okay. Number 44, these are the ones that have the exponent forms of the improper, not improper, what's the word phrase I'm looking for here? Anyway, this one's infinity to the 0 form. There's 0 to the 0, infinity to the 0, and indeterminate forms. That's what I'm looking for. Indeterminate forms. Infinity to the 0, 0 to the 0, and 1 to infinity. So yes, you put over 1 over 0 is considered infinity, so it's infinity raised to the 0. So this is where you have to assign some sort of variable name, not x, to the left side. It doesn't have to be y, but I generally use y in my notes. I mean, you could use any letter you really want as long as it's not x. So you're defining y then to equal that limit. So ultimately we're trying to find the value of y at the end. So you natural log both sides, which then allows for the exponent to come down, and then you can put the ln, sort of skipped a couple steps here, but you know, one of the things that's in my notes, you know, when the ln of a limit is the same thing as the limit of an ln. So you can automatically, even though the ln's on the outside, it's okay to put it here. That's mathematically correct. So I kind of brought that down all in one step. You can do the same thing too. Put the ln in front of what's in the parentheses, bring that coefficient down in front of the ln, then just leave the limit sitting out here to the outside. So after you do that step, you're always going to have a multiplication here, which means we drop something down. And as I said in the last problem, we are not ever dropping natural log. So multiplying by x is the same thing as dividing by 1 over x. Because divide by 1 over x, flip it over, that becomes x. So now here's a little trick here. You can actually, if you don't catch this little trick, and I did this in my notes for another problem. But the derivative of natural log of x, a natural log of u, basically is u prime over u. So I just wrote it like this step right here. I just wrote it as u prime 1 over x prime divided by 1 over x. Now the bottom, we're taking the derivative of 1 over x. So if you notice though, so without even actually taking the derivative of 1 over x here, I can look and see that those are common, those are they cancel. 1 over x prime divided by 1 over x prime would automatically cancel whether or not I actually take the derivative. I could take the derivative and then cancel it, but hey, why do extra work if we don't have to? So basically you're left with a 1 right here. 1 over 1 over x, like we have right there. And 1 over x just becomes x. So you're saying the limit as x goes to 0 of x equals 0. And it's real easy to think that 0 would be the answer here. But 0 is not the answer, because we're trying to find the answer for y. 0 is what ln of y equals, not y itself, because y itself is the limit. That's what we want. But we're close, though. That's the important thing, is we're close. So what you have to do every time is after you work this out and you get the numerical answer, you have to raise both sides to e. So e to the ln of y will get us y, which is what we want, our limit. So the answer is always going to be e raised to whatever number you get from this process. So in this case, the number was 0, so it would be e to the 0, which is 1. So the answer will be 1. So had you gotten 4, for example, when you worked out this limit, the answer would have been e to the 4th power. All right, let's look at number 45, same idea. We stick an ln in there, and we can bring that exponent x down all in one step, put it right in front of the ln. So we're working with this right here, and ln of y on the left side. And something has to drop, not ln. So we drop the x down and make it 1 over x. And so we have a similar type situation here. So we have du, u prime over u, so it's 1 plus 2x prime divided by 1 plus 2x, all over 1 over x prime. Now, if you don't catch this, that's okay. It would just save you a lot of time. But now keep in mind that the derivative of 1 is just 0, but 1 plus 2 over x all prime over 1 over x prime would just simplify to be 2. Because just think of it this way. The derivative of 1 would be 0, so you could ignore that. And remember from way back in Cal 1, if you take the derivative, let's say, of c times f of x in parentheses or bracket, that's the same thing as c times f prime of x, meaning I could pull the 2 out. So 2 times the derivative of 1 over x. So the 1 over x is canceled derivative, and you'd be left with 2. So that is correct. This would cancel to 2. So I have 2 plus 1 plus over 1 plus 2 over x, put in infinity. 1 plus 0 gives us 1. 2 over 1 is 2. And therefore, that's not the answer is not 2 to the final problem. It just means ln of y is 2. Therefore, y would be e to the 2. And here's number 46. And we natural log it, bring the x down, drop the x to the bottom to make it 1 over x. So we take the derivative of natural log of tan of x will be du over u. So the derivative of tan of x is sec squared of x over tan of x over -1 over x squared. And I flip this around a little bit to kind of get it out of complex fraction form to get it in one fraction. So x squared would jump up with sec squared x. And I took the negative up there. And then tan x just comes down the bottom, pairs up with 1, so it just stays tan x. So, well, there's different ways to go about this. I went ahead and went with a conversion to sine and cosine. So if you convert sec squared to 1 over cos squared, and you convert tan to sine over cosine, that'll flip over and you'll have a cosine on top and cosine squared on bottom, so it leaves a cosine on bottom, and then the sine will stay on the bottom. So that becomes 0 over 0, and which is L'Hopital's rule. So I took L'Hopital's rule for this one. Negative 2x on top. On the bottom, I used the product rule, sine times cosine. And so in other words, the derivative of sine would be cosine. Cos times cos is cos squared. Now you might think I messed up here because I have a negative. Either way, the product rule has a positive. But here's what's happening. When you go sine times the derivative of cosine, the derivative of cosine is negative sine. So sine times negative sine is negative sine squared. So now when I put 0 in there, I'll get 0 on top, as long as I don't have 0 on bottom, which I don't. I have 1 squared minus 0 squared, so I have 0 over 1. But 0 is not the answer. E to the 0 is the answer. So the actual answer would be e to the 0, which equals 1. So that concludes the L'Hopital's rule portion of the review problems.